To introduce Kristina Wicke, who's going to talk about the Colless balance for root trees. And she's currently doing a postdoc at Ohio State University, but I think in September, right? She's going to be local and be at New Jersey Institute of Technology, just across the river. So welcome, Kristina.
Okay, yeah. So thanks a lot for the introduction and invitation to speak here. So as Megan said, I'm currently a postdoc at Ohio State, and my research interest is mathematical phylogenetics. So I'm interested in developing theory for reconstructing and analyzing so-called phylogenetic trees and networks. And so one particular interest of me is studying structural and combinatorial properties of phylogenetic trees and networks. And in particular, recently I've looked into the so-called balance of trees and networks. And however, before I tell you more about the Colless index itself and its specific properties, let me briefly introduce what I mean by phylogenetics and phylogenetic trees. So very roughly speaking, if we think about phylogenetics, then phylogenetics is actually an area of biology, or more precisely evolutionary biology, that is concerned with studying and reconstructing the evolutionary relatedness and history among biological entities. So often these are species. You might be interested in reconstructing the evolution of all mammals, all birds, or even all living species on Earth. But it could also be certain lower level structures like protein complexes. And recently you might have seen phylogenies or phylogenetic trees of the COVID virus. And so usually these evolutionary relationships are then represented as so-called phylogenetic trees or evolutionary trees. And I'm giving two examples here. So on the left-hand side, you can see one of the oldest and most famous phylogenetic trees that was found in Charles Darwin's notebook, where he said, I think, and then we see this branching diagram here with this one maybe denoting the origin of life or of these species. And then we see this branching or tree diagram where branching occurs, and what we can see here is A, B, C, and D. So these A, B, C, and D might be present-day species. So Charles Darwin was one of the first to think of evolution as being a tree-like process. Nowadays, phylogenetic trees tend to look more like the one that you can see on the right-hand side with hundreds or thousands of species. So here it's hard to see, but this little arrow here indicates you are here. So this is where a human would place in this large phylogenetic tree. And so mathematically, or for my talk, what I mean by phylogenetic trees from a mathematical point of view, I will restrict the analysis to rooted binary phylogenetic trees, which are basically rooted trees whose leaves or the degree 1 vertices are labeled by some set X of species. And so this leaf labeling makes an ordinary graph theoretical tree a phylogenetic tree. And so they are rooted, so we have a root vertex denoted as rho within degree 0. And in this case, because the trees are binary, out degree 2. So every vertex has basically has degree 3, except for the root that has degree 2 and the leaves that have degree 1. And so such a tree would depict the evolutionary relatedness, in this case, of species 1, 2, 3, and 4. So the way we read such a tree is that the leaves correspond to present-day species 1, 2, 3, and 4. And then as we move back in time, internal vertices represent common ancestors. For instance, this vertex would be the ancestor of 1 and 2. This vertex is the last common ancestor of 3 and 4. And the root is the last common ancestor of 1, 2, 3, and 4. Okay, so very generally speaking, phylogenetic trees represent the evolutionary history or relatedness among a set of species. And so one main interest for biologists is, of course, to infer the actual tree, infer the relatedness and relationships among species. But then given a tree, it's also of interest to, on the one hand, study the branch length or infer the branch length, which means infer the timing of speciation events. And the second aspect that's of interest, and that's what I'm focusing on today, is understand or analyze the shape or topology of a tree, which biologically is determined by differences in the diversification rates among clades or among groups of organisms. And so in order to understand or to summarize the shape or topology of a tree, one popular measure that is used is to quantify the so-called balance or symmetry of a phylogenetic tree. Okay, so let me start with an example. Suppose we are given those two trees. on 8 leaves, then you will hopefully all agree that the left-hand tree looks way more balanced or symmetric than the right-hand tree, even just from a graph, a theoretical point of view. This tree has more automorphisms and so forth than the right-hand tree. Okay, so we would consider this tree probably more balanced than this other tree. And in fact, we call this tree the fully balanced tree, and this is considered to be perfectly balanced, whereas this tree, and this will appear later on, is called the caterpillar tree. And we usually think of the caterpillar tree as the most imbalanced tree that we can have. Okay, so for those 2 trees, we can look, it's kind of easy, or it's intuitive to say that the left-hand tree is more balanced than the right-hand tree. However, if we now look at those 2 trees, for instance, on 6 leaves, it's maybe a little bit harder to decide. Because if we start looking at the left-hand tree here, then it's very balanced locally. All pending subtrees are fully balanced, but at the root there's this certain imbalance in subtree sizes, because one subtree has 4 leaves, the other one has 2, and you can think of it's a little unbalanced or asymmetric. Whereas the other tree is perfectly balanced at the root. In particular, both subtrees are isomorphic in shape. So we have a perfect symmetry at the root, but then the 2 subtrees are actually caterpillar trees. And I just told you that we think of the caterpillar trees as the most imbalanced trees. So for those 2 examples, it's maybe a little bit harder to decide which one is more balanced, or if they are maybe equally balanced. And so in fact, this question of asking how balanced is a tree, can we order trees from imbalanced to balanced? This general question has led to the introduction of several balance indices. There are currently about 20 balance indices discussed. The Colless index and the second index are the oldest and most famous ones. And then there are newer indices like the total cophonetic index, the rooted quartet index, or the cherry index. And in this talk today, I'm going to focus on the Colless index, as this is probably the most popular index used in tree balance. And as it turns out, all those tree balance indices are usually invariant under permutations of the leaf labels. So in the following, we will ignore the specific species labeling the leaves and just think of the underlying graph theoretical tree, or we also call it a tree topology. Okay, so given such a rooted binary tree topology, Colless introduced the Colless index in 1982, and it's defined as follows. So what we do is we sum over all interior vertices of our tree. Let's call such an interior vertex V. And then what we consider is the local imbalance at this vertex V, measured in terms of the difference in subtree sizes rooted at the children of V. So maybe let's look at an example. So what we do is, for instance, for this tree, we sum over all interior vertices and we compare the subtree sizes of the 2 subtrees rooted at the children of a particular vertex. So for instance, for this red vertex here, we have this subtree of size 1, this subtree of size 1. So this gives us the 1 minus 1. Then for the green vertex, again, 1 minus 1. And for this blue vertex, so the blue vertex again has 2 children, the red and the green one. The red tree has size 2, the green tree also has size 2, so we get this 2 minus 2. Okay, so in total, the Colless index of this fully balanced tree would be 0. Whereas if we look at the caterpillar tree, again, we need to sum over all interior vertices. For this red one, we get 1 minus 1. For the green one, 2 minus 1. And for the blue one, 3 minus 1, and so 3 in total. Okay, does that make sense so far? Does the definition of the Colless index make sense? Okay, so that's the Colless index. And the idea is now the smaller the Colless index, the more balanced we consider the tree. Or in other words, the higher the Colless index, the more imbalanced the tree. Okay, so here is just some 2 basic properties of the Colless index that will be very useful subsequently. So what the first thing to note is that if we want to calculate the Colless index of a tree T, we can actually recursively calculate it by calculating the Colless index of its 2 pending subtrees. So here's a rooted binary tree T with root rho and 2 pending subtrees TA and TB. And so the Colless index of this complete or whole tree C of T is the Colless index of TA plus the Colless index of TB, and then plus this difference in subtree sizes. So NA denotes the number of leaves in TA, and NB denotes the number of leaves in TB. And this lemma is very straightforward to show it, because we can simply, since the Colless index was the sum over all interior vertices, we simply partition the set of interior vertices into those that are in TA and those that are in TB, and then we're left with the root. And so this gives this NA minus NB term. Okay, so that's a very straightforward property, but it turns out to be very useful in proofs, because then this allows you to prove things on induction, for example. And a consequence of this, the recursiveness of the Colless indexes also is the following statement. And this will be relevant as we're considering maximal and minimal trees. So here the statement is, suppose T is a rooted binary tree with n leaves, then T has minimum or maximum Colless index among all trees with n leaves. So Tn is the space of all leaves with n trees. If that is the case, then TA and TB must also have minimum and maximum Colless, respectively, maximum Colless index on their numbers of leaves respectively. If that was not the case, we could, for instance, if TA was not a minimal Colless tree, we could replace it with a minimal one on NA leaves, and in total obtain a smaller Colless index. Okay, so the central idea here is the Colless index is recursive, and an optimal tree will have optimal subtrees. And this holds for every level, so we can recurse down the tree. Okay, so that's these are two basic properties of the Colless index. And so when we started to look at this index, as I indicated, this index was introduced in 1982, and the paper had been cited several times. So several people used the Colless index, but what we realized is that certain properties of the Colless index were actually not known in the literature. So some statements were given, often without proofs, and one of my co-authors called that folklore knowledge about the Colless index. So I'll briefly summarize that before then introducing what we proved additionally. So one fact that was often stated was that a caterpillar tree on n leaves uniquely maximizes the Colless index, and the Colless index of this caterpillar tree is n-1 times n-2 over 2. Okay, and so here's the caterpillar tree. So it's not super hard to see that the Colless index of the caterpillar tree is actually this expression, because what we have is we need to sum over all the corresponding values for the interior vertices. So here for this one we get a factor of 0. Here for this one we get 2 minus 1 is 1. For this one we get 3 minus 1 is 2, and so forth. So this is actually this leads to the triangular numbers, or a triangular number, and the Colless index is in fact n-1 times n-2 over 2. And you can then show, for instance, by induction, that the caterpillar tree is in fact a unique tree that achieves this value. So again, this was stated several times, but a formal proof was in fact not given until 2018. Okay, so that was, in any case, the caterpillar tree uniquely maximizes the Colless index, so it's the unique most imbalanced tree according to the Colless index. What was also often stated in the literature without proof or just as an observation was the following. So suppose that n, our leaf number, is a power of 2, then the fully balanced tree uniquely minimizes the Colless index, and the Colless index is 0. And so for this one, that's also not hard to show. So suppose we have a fully balanced tree, then we can think about the Colless values for each vertex. They will all be 0 because it's fully balanced. So we have at each vertex, the numbers of descending leaves will be identical. So we get a sum of 0. So this is 0 in total. And the other direction, assume you have a tree with Colless index 0. Then, for instance, again, using induction, you can show that the tree must be a fully balanced or fully symmetric tree. Okay, however, this tree only exists if n is a power of 2. The leaf number is a power of 2. Okay, so these two things are kind of trivial and had been known before. However, there were still several open questions in the literature. In particular, while we knew the minimum value, namely 0, for leaf numbers that are powers of 2, what was not known was the minimum value of the Colless index for an arbitrary number, n of leaves. Moreover, it wasn't clear which trees have minimum Colless index. For instance, it wasn't clear if there's only one tree that minimizes the Colless index or if there are several trees. And then related to that, the number of trees with minimum Colless index was also not known. And so we were interested in analyzing those questions. So let's start with looking at the minimum value of the Colless index for arbitrary n. And just as a side remark, why are we even interested in that? Well, that knowing the maximum and minimum value for arbitrary n, for example, allows you to normalize the Colless index to the unit interval 0, 1 by the affine transformation. So this, for instance, allows you to compare the balance of trees with different numbers of leaves. So this is why it's relevant to know the minimum value of the Colless index, even also for arbitrary n. Okay, and so when we started looking at that, the first thing that we could prove is that the minimum Colless index, or the value of the minimum Colless index, if we let Cn denote this minimum value, then we can find a recursion to get this value. So if Cn denotes the minimum Colless index for a rooted binary tree with n leaves, then the sequence of these Cn values satisfies that C1 is 0. So the Colless index of a tree consisting only of one leaf or one vertex is 0. And for every n at least 2, we get this recursion. So we have that Cn is C of n over 2 ceiling plus C of n over 2 floor, and then we get the difference in leaf numbers, ceiling and floor. Or in other words, C of 2n is 2 times Cn, and C of 2n plus 1 is C of n plus 1 plus Cn plus 1. Okay, so this gives a recursion to calculate the minimum Colless index. And so once we had this recursion, we started to look at the sequence Cn, and here's a plot for these values. So here's the minimum Colless index for Cn for n 1 up to 128. And if I connect those dots, we get this interesting looking diagram. And so what we then did is we had the sequence, we plugged it into the OAs, the online encyclopedia of integer sequences, and we realized that there's a surprising connection between the minimum Colless index and a so-called and a fractal curve, the so-called Blancmange curve. So let me introduce this curve for you. So the Blancmange curve, it's also called the Takagi curve or the Takagi-Landsberg curve, is a fractal curve that is defined on the unit interval as this infinite sum. So we have the sum from I equals 0 to infinity of 2 to the minus I times s of 2 to the I times x, where s of x measures the distance from x to the nearest integer. Okay, and so this is how the graph of this function looks like. Apparently there's a French dessert called French pudding dessert called Blancmange, and apparently the curve mimics or looks similar to that dessert, so that's why it's called a Blancmange curve. Okay, however, it's this fractal curve, and what we can do is, as I said, it's an infinite sum, but we can look at partial sums. And so here are the first 6 partial sums. So if we only look at I equal to 0, then we get this triangle, which is the absolute value. If we take I equal to 0 and 1, we get this shape here. Going up to 2 gives this shape, and so forth. Okay, so if you now try to remember these shapes, I'll go back to the Colless index figure. And so what we see here is that these shapes occur in our figure. So here we have the triangle, then we have this thing that goes up, then the 2 top peaks, and so forth. And so while the Takagi curve is defined on the unit interval, our function is of course not defined on the unit interval, but our intervals are intervals between powers of 2. And so it turns out that this Takagi curve, the partial sums occur in our Colless intervals of powers of 2. More formally, what we then could show and what gives an explicit expression for the minimum Colless index is that if we let Kn denote the base 2 logarithm of n, and we round that up, and we let Tx denote the function whose graph defines the Blancmange or Takagi curve, then we could show that Cn is actually 2 to the Kn minus 1 times the Takagi curve evaluated at a certain point. Okay, so we get this surprising connection between the Colless index, and a concept from phylogenetics, and the Blancmange or Takagi curve, a concept that's, for example, been studied in numerical analysis, or this fractal curve. But on the other hand, with that, we now finally have a closed expression for the minimum Colless index, and we can in particular determine the minimum Colless index for any n without having to use a recursion. Okay, what we then also realized is that in fact there's a second equivalent expression of the minimum Colless index, which doesn't explicitly use the Takagi curve, but is based on the binary expansion of n instead. So if we consider the binary expansion of n, so we write n as the sum j equal 1 to L 2 to the mj, then we could prove that we can alternatively express the minimum Colless index as this sum here, involving the coefficients of the binary expansion. But of course, the two formulas are equivalent, as we're still talking about Cn. Okay, so with that, we could fill in the first gap in the literature. We could give a closed expression for the minimum value of the Colless index for arbitrary n. So then the question is, of course, how can we also tell something about the trees that achieve this minimum value? Is there always one tree? Are there several trees with minimum Colless index? And how do these trees look like? Okay, so what we can first note is that the tree is not necessarily unique. And in fact, here, the two trees I showed you in the beginning on 6 leaves, they both turn out to be minimal Colless trees among all trees with 6 leaves. So both of them have a Colless index of 2, and this is the minimum value that we can get on 6 leaves. So these are equally balanced, most balanced. So that then raises the question if we can characterize all trees that have minimum Colless index. And so for that, it's useful to recall this recursive definition or recursive computation of the Colless index. So recall that the Colless index of T can be expressed as the Colless index of TA plus the Colless index of TB plus this difference in leaf numbers. And so the idea is now that we're interested in characterizing valid ways of partitioning n, the number of leaves, into NA and NB. Okay, so for every n at least 2, we let QB of n denote the set of all pairs NA and NB, such that NA is at least as big as NB, and NB is at least 1, NA plus NB sum up to 1, and such that, and this is the important part, such that the corresponding Colless index we get for n leaves, if we sum up the minimal one for NA plus the minimal one for NB plus NA minus NB gives the minimum on n leaves. So we denote all pairs NA and NB that satisfy this criterion a valid pair. Okay, the idea is now that if we know the valid pairs, we can recurse down the tree and characterize all trees that are fully balanced, have minimum Colless index, that are most balanced. And we can also then recursively generate all those trees. And so the question is, can we characterize the set QBN of valid pairs? And it turns out that yes, we can do that. And here it's a long and technical statement, so I won't go through all the details. But what we basically do is we take our leaf number n. We first divide out the highest power of k that's included in n. So we let n0 be defined as n over 2 to the k, where k is the exponent of the largest power of 2 that divides n. And then we consider the binary expansion of n0. And based on that, we can then fully characterize the set QBN. So we have several conditions here. A, for instance, if n is the power of 2, then QBN only contains the pair n over 2 n over 2, which is what we already knew before, because we knew that for the fully balanced tree, there's only one way to get a minimum tree. But for the other, if n is not a power of 2, then we have certain rules of what elements will be contained in QBN. So if this pair will always be contained. And then we have several additional pairs. And then, as I said, it's not very useful to look at all the details here. But what we can show is that the pairs described in B1 up to B4 are all pairwise different. And in particular, QBN contains no other element. So we can fully characterize the trees with minimum Colless index. Okay, so we have this characterization of trees with minimum Colless index, and this directly leads to a recursive way to obtain all minimal Colless trees. And so the last question is can we also determine the number of trees with minimum Colless index? And so for that, what we currently have is a recursion, which is basically based on this way of recursively finding valid pairs. So here, if you now consider the sequence or C tilde of n, if that denotes the number of minimal Colless trees with n leaves, and we consider QB tilde of n to be all valid pairs in NA in QBN that satisfy that NA is strictly larger than NB, then we can get the following recursion for C tilde of n. C tilde of 1 is 1, because there's only one tree, and this is automatically minimal Colless. And we then have that C tilde of n is the sum over all pairs NA and NB in this set QBN tilde. And we simply multiply the number of minimal trees we have on NA leaves with the number of trees we have on NB leaves, because all possible combinations will give a minimal Colless tree. And then for the case that NA is equal to NB is equal to n over 2, we count the number of ways we can choose two minimal trees on n over 2 leaves and combine them into a tree on n leaves. So this is this last term here. Okay, so we have this recursion for the minimum Colless index. And so again, we can look at the curve, or we can plot these values. And here's what we get, again, for n equal to 1 up to 128. So this is this curve we get. For what we, for instance, see is that at powers of 2, as well as plus minus 1, there's always only one tree with minimum Colless index. For instance, here 15, 16, 17, there's only one tree. Then 31, 32, 33, and so forth. But other than that, we can see this curve, which again might be a fractal curve. Okay, so this however leads in fact to an open problem, because currently we only know, or we only have the recursion for the number of trees with minimum Colless index. However, an open problem or an open interesting question would be to ask whether we can find a closed expression for C tilde of n, and then to analyze if this seemingly fractal structure is really a fractal structure or maybe just an artifact of something. And if it is fractal, then can we maybe find a connection to the sequence Cn. So is there maybe a direct connection between the sequence Cn of minimal values and the sequence Cn tilde of minimal trees? Okay, however, I'll leave that. That's currently an open question. Okay, so now that we know the minimum value of the Colless index, we can characterize all trees, and we can at least recursively count the number of minimal trees. In the next few minutes, I'm going to focus a little bit more on two particular types of trees that minimize the Colless index, to give you a little bit of intuition of how these trees look like, apart from the QB description. Okay, so I'm going to introduce two extremal classes of minimal Colless trees, and the first one is called the class of maximally balanced trees. And so for this, it's actually useful to recall the recursive formula we obtained for the Colless index. The C of 2n is 2 times Cn, and C of 2n plus 1 is Cn plus 1 plus Cn plus 1, because this directly gives us a way to construct a minimal Colless tree. So essentially, if we have an even leaf number, say 6 in this case, what we do is we take our 6 leaves and split them into 2 sets of 3 leaves, and then we recurse. If we in this case have 7 leaves, we split into 4 and 3, and then we recurse. So and essentially at each step, we have our leaf number, and we try to split it into 2 subsets of as even size as possible. And so this leads to a class of trees that have been studied in the literature before, and these are the so-called maximally balanced trees. In fact, they're defined slightly differently via vertices, but the idea is identical. So in order to formally introduce the definition of the maximally balanced tree stated in the literature, if we consider balance values of vertices, so an interior vertex V with NV descendant leaves is called balanced when its two children have NV over 2 rounded up and NV over 2 rounded down leaves respectively. So this is just the idea I told you of splitting into as even subtree sizes as possible. And so a rooted binary tree T is then called maximally balanced if all its interior vertices are balanced. And you can show that for all n, there exists a unique maximally balanced tree up to isomorphism, and when we denote that as TMBN. And so the proposition or corollary maybe is that the maximally balanced trees are among the minimal Colless trees, or in other words, the Colless index of a maximally balanced tree on n leaves is Cn. And why did I say that these are extremal? Well, the maximally balanced trees are extremal in the following sense among all minimal Colless trees. They are extremal in the sense that any other minimal Colless tree will have the difference in subtree sizes at the root, or in fact at each vertex, will be at least as big as in the maximally balanced tree. And that's more a remark and doesn't require a lot of proof, because in the maximally balanced tree, we always try to have as equal, or try to have the subtree sizes as equal as possible to, and so this lower bound is not doesn't require proof. It immediately follows that any other tree will have either the same distribution in subtree sizes or split in subtree sizes or a bigger one. Okay, so however, the maximally balanced trees, if you think about intuitively, we start at the root and we always split into two sets of the leaves and try to keep the size as similar as possible. And so this is kind of a greedy from the top. What we then realized, there's another way to get minimal Colless trees, and we call that greedy from the bottom, because now instead of starting at the root, we actually start at individual leaves. So here, suppose we want to construct a tree on n leaves. So what we do is we start with n individual subtrees of size 1, so n leaves, and then we greedily merge 2 subtrees of minimal size until only 1 tree remains. Okay, so here's an example for n equal to 6. We start with 6 individual trees on 1 leaf, and now we greedily merge minimal subtrees. We would first merge 2 leaves, then again we can merge 2 individual ones. We can merge again. Now we have these 3 subtrees of size 2. We greedily merge 2 smallest ones, and we end up with this tree. And we call this the greedy from the bottom tree. And again, you can show that this is unique up to isomorphism. And so the greedy from the bottom trees are also Colless minimal trees, or in other words, the Colless index of the greedy from the bottom tree on n leaves is again Cn. And these trees now turn out to be extremal in the following sense. If we have a greedy from the bottom tree and consider any other minimal Colless tree on the same number of leaves, then the difference in subtree sizes in this other tree cannot be bigger than in the GFB tree. Okay, here's an example. On 12 leaves, that's the GFB tree, where we have 8 leaves on one side, 4 on the other. And so from this statement, we know that, for instance, dividing into 9 and 3 or 10 and 2 will never be possible. This will never give a minimal Colless tree. And so here, the idea is, or the intuition for that is that the difference in subtree sizes in the greedy from the bottom tree can be quite big. So for the root, the value we get for the Colless index would be 8 minus 4, which is 4, which is quite big for 12 leaves. However, the subtrees are locally very balanced, so we get a lot of zeros in the subtrees. And so that kind of balances out the large value we get at the root. However, we cannot make it larger. As I said, 9 versus 3, for instance, is not possible. Okay, so the GFB trees are extremal in the sense, and this statement requires a proof. So this is less straightforward to show than the other one for the maximally balanced tree. Okay, so these are the GFB trees, and they turn out to be extremal in another sense. Yeah, so that's just a corollary that we can conclude from the two statements. So any Colless minimal tree, the leaf numbers in the two subtrees will be bounded from the corresponding leaf numbers in the maximally balanced tree and the greedy from the bottom tree. Okay, so what I was hinting at is that the GFB trees are extremal in another sense, and this is related to the notion of symmetry vertices. So let me first introduce what I mean by a symmetry vertex. So if we have a rooted binary tree T, then we call an interior vertex V a symmetry vertex when the subtrees rooted at its children have the same shape or are isomorphic. And we denote by S of T the number of symmetry vertices in a tree. And this symmetry, the number of symmetry vertices is in fact also used as a balance index. So there's been a recent paper in, I think last year, where just counting the number of symmetry vertices was proposed as being a measure of tree balance. Okay, so here in this example for this tree, we would have 7 symmetry vertices depicted as these red vertices. All others are not symmetry vertices. In particular, for instance, this one is not a symmetry vertex because this subtree has size 2, this one only has size 1, so they cannot have the same shape. Okay, and so symmetry vertices are themselves interesting for tree balance. And so it turns out that we can, if we have a GFB tree, we can actually, without having to count the number, we don't have to look at the tree itself and count the number of symmetry vertices. We know that in a GFB tree, we always have n minus 1 minus m1 minus ml symmetry vertices. And these coefficients m1 and ml again come from the binary expansion of the leaf number. So that's the first thing, but the other thing, and that's what makes the GFB trees again extremal, is that if T is a minimal Colless tree with n leaves, that is not a GFB tree, then we know, or we can show that the number of symmetry vertices in T will be strictly smaller than the number of symmetry vertices in the GFB tree. Okay, so across all minimal Colless trees, the GFB trees have the most number of symmetry vertices. What we currently don't know is how minimal Colless trees with the minimum number of symmetry vertices look like. So another open problem would be the characterization of Colless minimal trees with the least number of symmetry vertices. What you might conjecture is that, well, the GFB trees were extremal and the maximally balanced trees were extremal for this leaf partitioning statement. So maybe as the GFB trees are extremal for the number of symmetry vertices, maybe the maximally balanced trees are the other extreme. And so that's a valid conjecture. However, it breaks I'll show you an example where it breaks. So here's an example. On 24 leaves, the maximally balanced tree has 15 symmetry vertices. And this tree here is also minimal Colless and only has 14 symmetry vertices. And so this is in fact the smallest counterexample to this conjecture. The first time the maximally balanced tree has not the least number of symmetry vertices. And the idea here is, if you look at those trees, they look very similar. So this tree, the left subtree is the same here. And the difference is the right-hand subtree. And what I basically did here in this upper tree, in the maximally balanced tree, this tree is maximally balanced, and this tree is maximally balanced on 6 leaves respectively. And what we do is we replace one of them with the greedy from the bottom tree. We can do that because both are minimal Colless, so both those, the upper and the lower tree will still both be minimal Colless. And what happens is that in this local tree, we have 3 symmetry vertices. In this lower one, we have 4 symmetry vertices, so we gain 1, but then we can destroy those 2 vertices being symmetry vertices, because now this one is no longer a symmetry vertex because the 2 trees are different. And then similar, this one is also no longer a symmetry vertex because those two trees are different. And so we gain one symmetry vertex, but we lose two. And so in total, this will have a smaller number of symmetry vertices. Okay, so again, it's an open problem to characterize all minimal Colless trees with the minimum number of symmetry vertices. Okay, so as I indicated earlier, there are several other indices. We just talked about the symmetry, counting the number of symmetry vertices. Another very famous index and also very popular is the second index. So the last question that I'm going to consider is, well, how does the Colless index compare to the second index? If we rank trees, for instance, from balanced to not balanced, using the Colless index and using the second index, will those two indices make the same decision? So in order to do that, let me briefly introduce the second index, and that was even introduced 10 years earlier than the Colless index, but somehow the Colless index is still a little bit more popular than the second index, at least in terms of the number of citations of those two papers. However, in order to define the second index, again, what we do is we consider a sum over all interior vertices of the tree. But now, instead of considering difference in subtree sizes, we simply sum up the number of leaves below that vertex. Or in other words, we sum up the number of leaves in the subtree rooted at this vertex U. Okay, again, looking at an example, for this fully balanced tree, for instance, we would get this red vertex has two descending leaves, so 2 plus 2 plus 4. And for the caterpillar tree, we get 2 plus 3 plus 4, which is 9. And so again, the value for the caterpillar tree is larger than the value for the fully balanced tree. Okay, and so in fact, even though the second index was introduced in 1972, similar to the Colless index, there was some folklore knowledge about it, like that the caterpillar tree is always the unique maximum, the fully balanced tree is the unique minimum, and so forth. But again, for instance, the minimum value for arbitrary n was not known. And so basically at the same time as we wrote this Colless paper, someone else wrote a similar paper about the second index, also characterizing it in like 2020, where the index was already introduced in 1972. But that's just a side remark. So for our question, the question of how these indices relate, what we can show is that if we have a rooted binary tree on n leaves with minimum Colless index, then it will also have minimum second index. The converse, however, is not true. So we can find trees with minimum second index that do not have minimum Colless index. And so the idea here is that for the second index, basically you can show, or if you recall for the Colless index, we had this leaf partitioning for the maximally balanced tree. That was one extreme, and the leaf partitioning for the really from the bottom tree was the other extreme. And so it turns out that for the second index, every pair n A and B within that range will lead to a second minimal tree. Whereas for the Colless index, this is not true. For the Colless index, we need this QBN this technical QBN characterization. Okay, so in particular, the Colless index is a little bit more restrictive in defining or in considering trees as balanced than the second index. Okay, so that's the connection to the second index. But then, as I said on the first slide, again, the Colless and second index, they are also not the only ones. There are at least 17 other indices discussed in the literature. And many of these indices are not fully understood yet. So there are many interesting open combinatorial and statistical questions. And so if you're interested in this in a second paper, we've recently provided a comprehensive survey of all those currently 19 indices. And that can be found in arXiv. And we've also created this website here that I'm briefly going to show you. Okay, so this is maybe not the nicest web design, but what we do here is we have this website where you can find information about all the indices, and we indicate open questions. So just to give you an example, this B1 index, which is again an old index introduced in 1992, but similar to the Colless index, it's not very well understood. So for instance, the their maximal value is currently only known when n is a power of 2, so that similar to the case of the Colless index, but we don't know the maximum value for arbitrary n. We don't know the trees that have a maximal value, and so forth. Okay, so there's a whole bunch of open questions here. And what I might mean by statistical open questions is that it is also often of interest to understand the expectation and variance of a balance index under certain models of tree evolution. So without going into the details here, there are two popular models of tree generation or tree evolution called the Yule model and the uniform model, and getting expressions for those balance indices, getting expressions for the expectation and variance of these balance indices is often a very hard problem. And there are many things still to do in this regard. So go back to this slide now. So yeah, the general message here is if you're interested in these kinds of questions, there's a lot more to do. Okay, so however, with that, I'd like to thank you for your attention, and I'd like to thank my co-authors, Tomás Coronado and Francesc Rosselló from the University of the Balearic Islands, and Mareike Fischer and Lina Herbst from the University of Greifswald. Okay, thank you. I'm happy to answer any questions, of course.
So let's bring Kristina. And then does anyone have any questions?
That's very nice, Kristina. You mentioned there are two models for random tree. You said one was the uniform model.
Mm-hmm.
Does that mean a uniform labeled model?
Yes, so under the uniform model, you consider all labeled trees, so all phylogenetic trees.
Where just the trees are, where just the leaves are labeled, right?
The leaves are, leaf labeled trees. And then each of those has uniform probability.
And what's the other model?
And yeah, the Yule model, that's a pure birth process. So basically you start, that first generates a tree topology. You start with, say, 2 leaves, then you pick one uniformly at random and let that split into 2 leaves.
Oh, I see. Mm-hmm.
And you again split and split and split until you reach your leaf number, and then you assign the leaf labels uniformly at random.
All right, so it's like a golden Watson tree of a particular type. Yeah. It would be interesting to know whether, for example, the big phylogenetic tree that you exhibited has more or less Colless index than a random tree.
Yeah, so that's actually where these balance indices are used for. Once you know the expectation and variance under certain evolutionary models, you can then, suppose you have a tree from data. The idea is then to develop hypothesis tests for testing whether your reconstructed or empirical tree is likely to have arisen from, like the Yule model, for instance, or the uniform model.
I had another thought that when you were talking about the number of what I would call twin pairs, right? So pairs of children that have the same isomorphic descendants. Yeah. Probably the first measure most people would think of for the amount of symmetry in the tree would be the size of the automorphism group. Have you made any connection between that and having, say, low Colless index?
We haven't looked into that, so that's a good idea. Yeah, a good direction. So there's, as I said, there's this symmetry nodes index, which just counts the number of vertices inducing automorphisms. Then there's another index called the rooted quartet index that basically takes your tree on n leaves and considers all possible subtrees on 4 leaves. And for all these 4-leaf subtrees, it counts the number of automorphisms and then sums that up over. And so this also works for non-binary or trees where we have multifurcations. But yeah, so that maybe it would be good to start looking into at that direction of how these 2 indices compare.
Oh, thank you.
Yeah, thanks for that talk. That's really interesting stuff. I had a question about, you said that the minimum Colless index you could compute using the Takagi curve without the recursion, but the Takagi curve is defined by an infinite sum. So can you really plug in values into the Takagi curve and get the output?
Oh, okay, yeah. So I was maybe, yeah, okay, the idea is that we can show that certain, only at the first, say, L summons are relevant, and because all others will evaluate to 0. So we know where to cut off the sum, and so it will be, in fact, a partial sum of the Takagi curve.
Okay, thanks.
Yeah, yeah.
And then just one comment, so that sequence CN, it appears to be what's called a 2 regular sequence. Do you know about these sequences? So they're, I mean, when you showed those pictures, I mean, that's characteristic of these sequences. So here's a link to the Wikipedia page for K regular sequences. So these are analogous to sequences that satisfy a linear recurrence with constant coefficients like Fibonacci, but instead of relating, say, S of n to shifts of the sequence, S of n plus 1 or S of n plus 2, it relates the sequence into shifts sort of in a different base. So for example, here you might relate S of n to S of 2n or S of 2n plus 1. So that's what's coming up in your recurrence. So there's a whole class of these sequences. So I mean, it's you know, it might just be interesting to sort of fit this into that class.
Okay, thanks. That's a very good suggestion. Yeah. It might also maybe help for this open problem about where we're not sure if the number of Colless minimal trees also is related to some fractal curve, for instance.
Right. So you showed a log plot of that. Was that right?
No, it wasn't log. It was the actual numbers. Let me go back to that. So yeah, it's the actual numbers. So n is the leaf number, and then here you can see the number of trees.
So the vertical axis, I guess, is on a log scale.
Oh yes, yeah. So
yeah. So that's really surprising to me that when you take a logarithm, you get this nice nested structure. So yeah, it might help. But that's that's cool.
Are there other questions? If no one else has one, so I have actually one. So Kristina, so you kind of gave the characterization in terms of kind of these very technical equations, right? And then you showed us the 2 different classes. And I was just wondering, do you know what like proportion of the total number of minimal coalescent, or not coalescent, minimal coalesce trees the 2 extremal classes you showed us like cover?
Okay. So you mean the maximally balanced and the greedy from the bottom? You mean those 2 classes?
Yeah. Like basically what like, because those are like nice descriptions of them, right? And then your other, like the actual characterization is like kind of very technical, right? And I was just curious, like, how many trees are you missing that are not kind of like nicely described?
Oh, I think a lot, because the maximally balanced and greedy from the bottom are just two particular trees. But as we see in this plot here, for the number of minimal Colless trees grows rapidly, but we're not. But the greedy from the bottom.
Oh, okay. Maybe I did it.
One
But greedy from the bottom, there's not like for any n, there's only one greedy from the bottom, or there are multiple ones.
It's also.
Okay.
Yeah.
Oh, okay. I think I was thinking that was a class of trees itself.
Oh no, sorry. It's also unique.
No. Oh, okay. I see. Okay, so those 2 are just 2 of them, and then there's like all these other ones.
Yeah.
Oh, interesting.
Yeah.
Wow. Okay. I do have other classes.
Sorry. Once you can.
Oh, is this correct? Sorry, go ahead.
Yeah, I was just saying, once you get bigger, you can then even start combining maximally balanced and greedy from the bottom subtrees, and that already gives you several new trees that are neither one of them, and then there's other ones. Yeah.
Okay. Wow. Okay. Very interesting. So last call if anyone has any other questions. Okay. And then thank you very much for your talk, then, Kristina. So let's thank our speaker one more time.